Okay, so if I can click this. Again, I think this is about as good as we're going to get size-wise for today, but hopefully you can see that, and if not, feel free to scoot further down. So today we're going to continue talking about probability with discrete random variables, and hopefully we'll also get to the continuous random variable case if we go efficiently enough. So speaking of inefficiency, I got to tell you that I'm an employee of Columbia University. I'm also a co-founder of Stan Group, a startup that provides support, consulting, etc. for businesses using Stan. And according to Columbia University policy, those two things together require that these facts be disclosed in any and all public presentations. Okay, so the goal for the class today is to learn about expectations, which is a very important operation that you can do on a probability distribution, and to generalize what we learned last time about discrete random variables, such as the number of pins you knock down in a roll of bowling, to continuous random variables, such as the amount of time elapsed, or income, GDP, or beliefs about unknown parameters, like the coefficient in a regression, can be thought of as continuous random variables. And this is particularly important because Stan, which we'll learn about in a few months, only works with unknown things that you want to get the posterior distribution of that are continuous. Data that you condition on are allowed to be discrete, but the unknown parameters are assumed to be unknown and continuous. So we need to learn more about that case. And it's going to be helpful to learn about all such cases if we get everybody reading, and even more important than reading, posting, and even more important than posting questions, answering questions on Piazza. Now, over the weekend and last week, there are a number of you who posted some stuff, and that was all right, but there's most of you who didn't post anything, so you're currently in the hole in terms of class participation. But moreover, it's a good opportunity to fill in gaps in your understanding. Like I said, we're going through a semester of probability in about 3 weeks. It's inconceivable that no one has questions about the concepts and ideas that we're talking about, and to be able to do those outside of class, online, where everyone can benefit and contribute to the answer, ask follow-up questions, is a really important tool that is going to be necessary for a class that deals with these many topics in this, detailed a fashion, over the course of the semester. So get in the practice of reading that. If you have a question, whether it's about the reading of the lecture or, more broadly, Bayesianism, anything like that, you can post, and ideally we'll get a discussion going on those sorts of things. Okay, so just to review a bit from last time, we learned how to construct a joint probability distribution by multiplying marginal probabilities by conditional probabilities, where we condition on the thing that just happened. So the probability that A and B both occur can be written as the probability that B occurs times the probability that A occurs, given that the B has occurred, or something from B has occurred. And in R, we made that 11 by 11 table called joint underscore PR for a frame, which is to say 2 rolls of bowling. When we did this using random numbers rather than analytical calculations, first we drew from the sample space of the first roll with probability of knocking down x1 out of n pins. And that function was given by this ratio of Fibonacci's. To simulate the second roll, we drew from, again, the sample space, but with conditional probability of knocking down x2 pins, given that we knocked down x1 pins on the first roll, and we started with 10. So that's how we construct a bivariate or a joint distribution. But sometimes we want to deconstruct a bivariate or a joint distribution into its marginal distributions. And to do that analytically in the discrete case, you sum over all the possible values on the margin that is of interest to you. So when we wanted the probability of knocking down x2 pins on the second roll, without specifying what happened on the first roll, we had to sum down the columns of that 11 by 11 table to get the probability of knocking down X2 pins on the second roll. But when we do simulations, we've already drawn from the joint distribution of roll 1 and roll 2. So we just need to analyze the vector. In this case, we did like 10 million of second rolls, and that will tell us anything that we want to know about the marginal distribution of the second roll. And so a lot of times working with simulations is easier than working with algebra. Any questions from last time? Oh, all right. So we mentioned we want to get into expectations. And the expectation operator is both very important and not very well understood. And that's in part because if English is your first or your second language, the word expectation means something a little bit different in this context. So the first thing we have to do is distinguish what the expectation is not. It is not the mode, because the mode is the element of the sample space, omega, that has the highest probability. So in the case of a first roll of a frame of bowling, the way we constructed it last time, a strike was the most probable thing to happen out of the 11 things that could happen on the first roll of a frame of bowling. That is the mode, or the modal outcome. That is not the expectation, even though in English, expectation sort of has a little bit of a different connotation. So if I say, I expect you to do the reading, the sort of most likely thing to happen is that you will do the reading. But that is not an expectation in the statistical sense. That is the mode. And the mode is not particularly useful, although in some circumstances it is. So neither the mode nor the expectation are the median of a probability distribution. The median of a probability distribution is the smallest element of the sample space, such that there's at least 50% chance that it's going to be less than that, and 50% chance that it's going to be more than that. In the case of a first roll of a frame of bowling, I believe the median was 9. It may have been 8. In any event, let's say it's 9. You had at least a 50% chance of getting a 9 or lower, and whatever is the remaining chance of getting something higher than a 9, which in this case is only 10. So the median is pretty well understood thing. It's not the mode when the distribution is asymmetric, but neither is it the expectation or the mean. So the expectation of a discrete random variable x, remember x, capital X, is a random variable, and a random variable is a function. The expectation of that random variable x is defined in the context of probability as the sum over the entire sample space of the product of x times the probability of x. So we take each element of the sample space. In the case of a first roll of a frame of bowling, that's 11 things that can happen, 0, 1, 2, all the way up to 10. We take each of those numbers, multiply them by the corresponding probability that that number of pins gets knocked down, and sum all those pairwise products up over the entire sample space. So we have a sum of 11 products. That is defined in terms of probability as the expectation of x, or the expectation of whatever you're talking about. First roll of a frame of bowling, whatever. So the expectation of the first roll of a frame of bowling is going to be, some, we'll figure it out in a second, number smaller than 10, definitely, because we're putting some probability although a small amount of probability on 0, 1, 2, etc., and adding those all up. So the expectation, it's so fundamental in probability that it has a special Greek letter, which is the lowercase letter mu. So if you see mu, it almost always refers to the expectation of a random variable. And in the discrete case, that's going to be a probability weighted sum. So we're weighting little x by the probability that little x occurs, and we're summing all those products together over the whole sample space. So questions about what an expectation is, you just have to memorize the definition of it. It doesn't correspond that well to English. Yes?
Okay, so in the case where the discrete random variable is the classification, and then the x and y's are sort of arbitrary, is the mode the expectation then?
No. So you're referring to the case where x can only be 0 or 1?
No, like if it's something other than numbers. Like
Oh, that way. So yes. The expectation, if you're just saying like for something that isn't well defined for multiple cases. So let's say the random variable I'm thinking of is what is the race of the person.
Right.
Let's think about that, and we haven't really got into this, as let's say the census defines 5 race categories, those all being 0, 1 variables, in which case the expectation of that is also going to be a vector. And because those are defined as 0s and 1s, the probability of each of those is going to be some interior number, like 0 times some probability, that's 0, plus 1 times some probability. It just comes back as the probability. But we'll get to a way of conceptualizing a nominal variable like that next week. All right?
Question on rotation would be also, because mu is sometimes also referred to as the mean.
Yes.
Do we also call this the mean then?
Yes, those are synonyms, but you don't want to confuse the expectation, which is a property of the function, with your sample mean estimator, which is like the sum of all the things in your data set divided by n. The sample mean estimator is an estimator of mu. But we want to think about the concept now rather than the estimator. So yes, expectation and mean are sort of interchangeable, but just, you know, emphasize you're talking about the function rather than an estimate. All right? This is just something you got to memorize. And if I use conditional probabilities, like the probability of x given y or given z, whatever it may be, then I get a conditional expectation, but it's the same thing. I multiply x by the conditional probability of x given something, and I get the conditional mean of x given that thing. So you can insert conditional probabilities to get a conditional expectation. It's the same operation. Sum of product over the whole sample space. Got it? So how would we calculate the expectation of the second roll of a frame of bowling? What are we going to need to do that? Yes. In this case, it would be unconditional probabilities because I haven't told you what happens on the first roll. But you're going to need probabilities. So where do the marginal probabilities of the second roll come from? Sum down the columns. Okay, and then we're going to multiply. So here I put that in math. We get the joint probability, and we're going to sum that over x1. And so that gives us the probabilities, and then the expectation of the second roll of a frame of bowling. I'm just going to take 0 times the probability, marginal probability of 0, 1 times the marginal probability of 1, etc., all the way up to 10, and I'm going to get some number. So in our code, I do column sums of the joint probability 11 by 11 table. I apply the definition of an expectation. I just do sum of omega times the probability of that thing happening on x2. and I get expectation of the number of pins knocked down as 1.064386. So nobody in the history of bowling has knocked down 1.06 pins. The expectation, even of a discrete random variable, is a real number. And that automatically distinguishes it from the mode, which is going to be an integer in this case, between 0 and 10. And also, in the case of an odd number of things that can happen, the median in this case is also going to be an integer. But the expectation is not, because you're multiplying probabilities, which are real numbers, by integers, and the product of a real and an integer is a real, and you're summing up a bunch of real numbers, and you get, in this case, 1.06. So you expect a little bit more than one pin to be knocked down on the second roll of a frame of bowling for a good bowler. And the intuition behind that is that there's not that many pins left over in the second roll to knock down. All right. We can also do this with simulations of random numbers. So I simulated 10 million frames of bowling last time. I had a vector called roll 2. And in the case where you have a large number of simulations, you can simply take the sample mean of that using the mean function in R, and it will be an extremely good estimator of the thing that you're trying to estimate. So it's correct to like 2 decimal places, which is, plenty. It's even, correct to 1 decimal place would probably be plenty accurate for social science purposes. But we can get as accurate as we want by doing more and more simulations. Got it? The hard part here is getting the probabilities. Multiplying and summing is something that you've been doing for 20 years now. All right? Okay. Moreover, this idea of an expectation applies to any function of a discrete random variable. I'm going to call an arbitrary function by g. So this is some function of x. And if we want to know the expectation of some function of x, we multiply that function by the probability that little x occurs, little x being the input to the function g, and we sum it up over all of omega. That is the expectation of a function. And there are some g functions that are so fundamental that they have their own names. So one that is not particularly interesting is when g is a constant, so it doesn't actually depend on x. A little algebra shows you can pull out the c. The sum of the probabilities over the whole sample space is 1. So you have c times 1. The expectation of a constant is that constant, which ought to be pretty intuitive. What we just learned on the previous slide is actually a special case of the taking an expectation of the function, where the g function is merely the identity function. So g of x equal to x, multiply that by the probability, sum it all up, you get the expectation. So if someone says the expectation, they're referring to mu. If someone says an expectation of some function, then they might be referring to something else. So probably the second most important function that we might take the expectation over is the function g of x is equal to x minus mu quantity squared. The expectation of that function is called the variance of the random variable x. It also has a special symbol, lowercase Greek letter sigma squared. That's the variance of x. It can be shown that the variance of the x, is equal to the expectation of the square of x minus the square of the expectation. That's a theorem, not a definition, but it can certainly be shown. So the variance of the x is an important measure, basically quantifying in squared units how much you expect x to differ from its own mean or expectation, mu. So it's a measure of a spread in a random variable. It's probably not the most common measure of spread. The standard deviation, which is defined as the square root of the variance, is a more popular measure of spread because it has the same units as x does. The variance is going to be in terms of squared units, which is usually not as intuitive, like what's a squared dollar or a square inch actually is used in, interior decorating and stuff like that. But for most cases, squared units are less intuitive than the units that the original x variable is measured. And by taking the square root, we get standard deviation that is in the same units of x. But a standard deviation is not an expectation. A variance is an expectation, and the square root of the variance is the standard deviation. Another function that's actually very important for Bayesian statistics, we'll get to later, is negative logarithm probability of x. We can multiply that function by the probability of x, sum it up over the entire sample space, and we get something called the entropy of x. And just as a preview, the entropy is an important quantity because it is maximized in the case of a discrete uniform distribution. So it's like for dice. Every face of the dice has an equal probability of coming face up. That is the distribution that maximizes the entropy, where entropy is defined this way. And loosely speaking, distributions that have more entropy are entailing weaker assumptions, weaker prior information about that variable. So you don't want your prior or anything to be weaker than what you actually know to be the case. But in a lot of circumstances, you want to choose a prior that has fairly minimal amounts of information or assumptions embedded in it. And the entropy is a good way of quantifying how uninformative a particular distribution is. And you might want to use that as one way of choosing a prior distribution to reflect your belief about something that you don't know very much about currently. So we'll get back to entropy, but I just want to point it out as another function that we can take the expectation over. Questions about expectations of functions? It's really the same process. Yes. Maximal entropy corresponds to weaker assumptions. This is often it's negative of what you might think of as entropy from like an information or engineering thing. So probability people define it the other way around, but still like whatever you say high or low is pretty arbitrary. Probability theorists do it differently. Okay. So the same thing applies to expectations of functions of more than one discrete random variable. So if I have two rolls in a frame of bowling and I want to calculate the expectation of some function of them, like their sum or some other thing, all I have to do is multiply my function by the joint probability that x1 and x2 both happen and sum it up over both sample spaces. So in the case of two discrete random variables, it's a double summation over both of their sample spaces rather than a single summation over the sample space of one thing or one function in isolation. So examples of bivariate functions whose expectations are important include the function x1 minus mu1. So the mu1 is the expectation of the first variable. That quantity multiplied by the quantity x2 minus mu2. The expectation of that function has a special name, and it's called covariance. Covariance is not used as much as correlation, again, because it depends on the units in which x1 and x2 are measured. So perhaps a more useful function to take the expectation of is not merely, the product of x1 minus its difference multiplied by x2 minus its difference, but to divide those two terms by their respective standard deviations. So we have the quantity x1 minus mu1 all divided by sigma 1, where sigma 1 is the standard deviation of the first roll of a frame of bowling, or whatever the first variable is, multiplied by the same thing, but referring to the second variable. So x2 minus its expectation, all divided by its standard deviation. The expectation of that function is known as the correlation, and it is typically denoted by the Greek lowercase letter rho, which looks like the American letter P, but is actually the Greek letter rho. Don't get confused about that. So both covariance and correlation measure linear dependence between x1 and x2. Correlation is restricted to be between -1 and 1 and is unit free. That's because the units of x1 and the units of sigma are the same, so they cancel when we do the division. So correlation is a unit free measure, whereas covariance embeds the units in which x1 and x2 are measured. So it's in units that are the product of those two units, often not really exactly what you want. So in the case of two consecutive rolls in the same frame of bowling, do you think the correlation is positive, 0, or negative between two rolls in a frame? Why is that? Right. So if you exceed your mean the first time, there's an unusually low number of pins available the second time. And so you will often fail to achieve your marginal mean on the second roll. And so that's going to get multiplied. So that's going to have some probability. Add all those up. It's basically, you're usually multiplying a negative number by the probability, which is a positive number. Negative times a positive is negative. You sum up over both sample spaces a bunch of negative numbers. You'll tend to get a negative expectation. And we can actually calculate that in R. So first, we're going to need the probability, the marginal probability of x1. I call that PR underscore x1. We use that to come up with the expectation of the first roll of a frame of bowling, EX1. And then I'm going to evaluate my G function into a G matrix using this outer business. This is really just a shortcut. All it does is take omega minus mu1 and multiply it by omega minus mu2 for all pairs of that. So again, you get an 11 by 11 matrix, which has in each cell the product of x1 minus mu1 times x2 minus mu2 for all possible combinations, or even some impossible combinations of x1 and x2. But that's okay, because the impossible ones are going to get multiplied by 0 when I construct the covariance. So the G matrix, is 11 by 11. And then I obtain the covariance by summing over all 121 things of the joint probability table, which is 11 by 11, times the G matrix, which is 11 by 11. Here I'm doing element-wise multiplication rather than matrix multiplication. We'll get to matrix multiplication next week. So joint PR times G matrix is also going to be 11 by 11. I sum over all the elements of that, and I obtain the covariance of two rolls in the same frame of bowling. Now, in order to get the correlation, I need to divide that by the respective standard deviations to get a standard deviation, I first need to start with the variance. So I calculate var underscore x1, the variance of the first roll of a frame of bowling, by taking the sum of the quantity omega minus mu1 squared, and then multiply it by the marginal probabilities of knocking down x1 pins on the first roll. I sum that up over all elements of omega. I get the variance of the first roll of a frame of bowling. Then I do the same thing for the second roll, only difference being I'm subtracting mu2 rather than mu1, and I'm multiplying by the marginal probability in the second roll of a frame of bowling rather than the first. So the variance of the first roll is much larger than the variance of the second roll, because for a good bowler, there's not that many pins to knock down, so everything is more compressed, less dispersed. Once I have those two variances, I can take their square roots to get the standard deviation and divide the covariance by the two standard deviations in order to get the correlation between the first and second roll of a frame of bowling. So I take the square roots of the product of the variances, that's like dividing by the standard deviations, and I have this correlation, which in fact is negative, and highly so, negative 0.88. That's 441458. That's the exact calculation, although that took about 8 steps. Given that I've already simulated a billion, or not a billion, but 10 million frames of bowling, I can just use the core function in R, which estimates the correlation. But if I have 10 million observations, it's going to be estimated very accurately, in this case, to 3 decimal places. So I could have skipped all that algebra just by having, a lot of simulations of frames of bowling. But the algebra is instructive because it follows directly from the definitions of all of these concepts. Expectation of a function for different functions, and extending it to the case where we have 2 variables, getting the covariance, going from the covariance to the correlation. These are all sort of fundamental operations on probability distributions that we're going to need to be familiar with as the semester goes on. So questions either about the ideas or even about the R code here? Yes?
Is there a perfect linear relationship between 2 consecutive poles?
No, not perfect linear. So, what happens on the first roll doesn't tell me exactly what's going to happen on the second roll. There's still randomness to it, unless I get a strike on the first roll, and then I'm guaranteed to get a 0 on the second roll, the way we're defining it. But no, both of those are, neither of those are deterministic, not even conditionally so. Other questions? All right. So if there's only 1 pin remaining, the way we've been defining it, it's going to be the first Fibonacci number divided by the third Fibonacci number minus 1. That's going to come out to 1/2. That doesn't seem particularly reasonable for a very good bowler, but it's one of many ways in which we could assign a probability to knocking down a single pin. And Bruno De Finetti, like I was talking about on the first day, proved a famous theorem, which is if you have independent binary events, so your sample space is just 0 or 1, the probability and those events are exchangeable, which is basically to say that the order in which they occur doesn't provide you any information. Then the appropriate distribution to use is the Bernoulli distribution. So the Bernoulli distribution is named for Jacob Bernoulli. It's defined for a sample space omega is the set 0 and 1. So this is a binary variable or a dummy variable. The probability that 1 occurs, 1 is usually denoted as like success and 0 is failure. So the probability of success given this unknown parameter p. P is an unknown between 0 and 1. So the probability of success is p. Consequently, the probability of failure is 1 minus p. It's the complement of that. And you'll often see the Bernoulli distribution written more succinctly as the probability of little x given p is p raised to the power of little x multiplied by the quantity 1 minus p raised to the power of 1 minus x. And that holds true whether you say little x is 0 or little x is 1. This sort of exploits the fact that any number raised to the power of 0 is 1. And any number raised to the power of 1 is just that number. So really we have a piecewise function here, but we can write it as a product of exponents, p to the x times 1 minus p to the power 1 minus x. Okay, so if this is the function that tells us the probability that x is 0 or that x is 1, what is the expectation of a Bernoulli random variable? And why is that? How do we arrive at that?
Formula.
Yes. So 0 times p is plus 1 times p is, and altogether that gives us, right. So the expectation of a Bernoulli random variable is p. P is typically a real number between 0 and 1. It could be exactly 0, it could be exactly 1, but that's sort of an edge case. So again, the random variable x can only be 0 or 1. Those are two integers. The expectation of x is a real number between 0 and 1. All right, so it's going to have a mode that's either 0 or 1. It's going to have a median. It'll be 0. But the expectation is going to be some number between 0 and 1. Okay? What is the expectation, or what is the expression for the variance of a Bernoulli random variable? Anybody have any ideas as to how you would go about calculating the variance of a Bernoulli random variable? Anyone want to give the definition of variance?
Just to the ex squared minus ex whole square.
Yes. So here we're talking about the theorem that was mentioned a couple slides ago. Variance is equal to expectation of the square of x minus the square of the expectation. So variables that are only 0 or 1 are easy to square. What's the square of a Bernoulli random variable? No. X is the Bernoulli random variable. So what's the square of x in this case? X. 0 squared is 0. 1 squared is 1. So a square of a Bernoulli random variable is equal to that Bernoulli random variable. So this simplifies to the expectation of x, which is p. All right, so we have p minus P squared. Otherwise equal to P times 1 minus P. P times 1 minus P is the variance of a Bernoulli random variable. Not that hard, but important. So if you have any questions about that, now would be a good time to ask. So this is often a good way, but usually x squared is not equal to x. So you're going to have to figure out what the expectation of the square of x is. But there'll be other opportunities for you to calculate variance. Got it? Does she have it? Yeah? Okay. We'll go on it. The binomial distribution. So a binomial random variable can be characterized as the sum of little n independent Bernoulli random variables. So in this case, the sample space of a binomial random variable is going to be what? I didn't write it down on the slide for some reason. Sample space, binomial random variable, it being the sum of n Bernoulli random variables.
0 to 2.
Up to n. So yes, 0 up to n, the integers. It's the omega for a Bernoulli binomial random variable. The probability of getting x successes out of n tries under a binomial random variable can be written as n choose x. That's the function that's like a fraction but without the bar there. The n choose x function can be written as n factorial divided by x factorial divided by the quantity n minus x factorial. That's the number of ways that x successes can occur in n trials if we don't worry about the order. So we have n choose x multiplied by p raised to the power of x multiplied by 1 minus p raised to the power n minus x, where x is typically the number of successes and n minus x is the number of failures. Although that function characterizing the probability of a Bernoulli random variable coming up as little x is not terribly complicated, it's already implemented in R by the d binom function, which inputs to it x, n, and p. And you get out the expression given here. The d binom function in R can also be used to evaluate the probability of a Bernoulli random variable if you set n equal to 1. So Bernoulli random variable is a special case of a binomial random variable with n equal to 1. But in general, a binomial random variable is the sum of n independent Bernoulli random variables, and sometimes n is greater than 1. N can be whatever you want. Because the expectation operator is just summation and multiplication, it's not too hard to show that for a binomial random variable, the expectation, mu, is equal to n times p. Stands to reason because the expectation of a Bernoulli is p. We have n of them, and they're independent of each other. So it's easy to show you can just multiply by n and get the expectation of a binomial random variable. Moreover, also easy to show that the variance of a binomial random variable is n times the variance of a Bernoulli random variable. So now we have n times P times the quantity 1 minus P. And we can substitute mu for NP if we want. All right? So why is the binomial distribution completely inappropriate for, let's say, modeling the first roll of a frame of bowling? Yes?
You have 10 possible outcomes. 0, 1.
Well, it's actually 11, but I can think of each pin. So do I knock down the head pin 0, 1? Do I knock down the one behind it 0, 1? So that by itself, I don't think is a super compelling reason why the binomial distribution should not be used to model bowling. Nigel?
Not independent, because if you get the means that you want to hit the second thing.
Correct. Bowling pins, not independent of each other. People in a survey, maybe. Might be reasonable to consider frames independent of each other, but not two rolls within the same frame, or not one roll. So binomial distribution probably less reasonable than the Fibonacci thing that we started off with for bowling. But the Fibonacci thing doesn't tell you the probability of knocking down an individual pin, just, X pins collectively. So we started with the case of bowling because it's relatively easy. Only 11 things can happen. But what if there was no upper bound on the number of things that could occur? So the number of eruptions of a volcano. There's no physical limit why, that could only be 10 or something like that. So in that situation, you could think of doing a binomial distribution as n goes to infinity. However, that doesn't seem too attractive because the expectation of that binomial distribution, n times p, would also go to infinity for any fixed p. So the trick here is to think about the limit as p, the probability of success on any individual trial, approaches 0, while the number of trials approaches infinity in such a way, at just the perfect rate, so that the expectation, which is n times p, remains constant. So p is getting smaller, n is getting bigger, np remains the same, and it remains mu. In this situation, we obtain a distribution known as the Poisson distribution. The probability, what's the sample space of a Poisson? The non-negative integers. And the probability of getting x, where x could be 7 or whatever, given this fixed mu, is mu to the x times e, the number e, 2.78128. Everybody know e? It's got to be like one of the top 5 most important numbers out there. Everybody's cool with that? So the Euler's number, e raised to the power negative mu, all divided by factorial of x. It can be shown that this is a valid probability function. If you sum it up, take the summation of that, inserting x 0, 1 up to infinity, it converges to 1. So some non-negative integer guaranteed to occur. And this is the probability function for a Poisson distribution, which is implemented in a more arithmetically stable way in R by the dPoIS function, which is going to input x and the mean. However, the mean argument in R is called lambda for historical reasons. All right. So what is the variance of a Poisson random variable? What? You? I know someone said the right answer, but I didn't hear who. Who said mu? Yes. Why?
So just to remember.
You just remember. So you're saying you just remember from the previous slide? I think you did. Because the variance of a binomial is NP times 1 minus P. We can substitute mu for NP and take the limit of this as P goes to 0. And we get, as was remembered in the front row here, mu. Poisson distribution is the only one whose mean and variance are equal to the same number. Nevertheless, the expectation and the variance are different concepts. They're always different concepts. They happen to be the same number in this one very special case. And this is actually unfortunate for its usage in social science, but it's kind of an interesting mathematical oddity. Questions about the Poisson or how I derived it as a limiting case of a binomial? I didn't really show you the derivation, but you can trust me on that or look it up on Wikipedia. All right. So what we've referred to as this probability function. So in the case of bowling, it was a ratio of Fibonacci's with like a -1 in the denominator there. I just put one up for a Poisson, mu to the x times e to the negative mu divided by x factorial. These functions that tell us the probability that x occurs for this or that distribution have a special name. They're known as probability mass functions in the case of a discrete random variable, often abbreviated PMF. And henceforth, I'm going to denote them with the function little f. So the little f function, I'm not going to use for just any old function. I'm just going to use it for these functions relating to probability. There's also a subscript that comes after the little f that seems redundant now, but I'll try to put it in because it emphasizes what the random variable is. So this probability mass function could depend on some unknown parameters, which are generically denoted theta. In the case of a Poisson, theta is usually instead given as mu, or even more often lambda. Which Greek letter you choose is kind of arbitrary, at least if you're not Greek. But anyway, I can write out these functions, and when I'm just referring it to a generic probability mass function, I'll usually use theta as the parameter, but theta could actually even be a vector of more than one parameter as well. The cumulative mass function, often abbreviated CMF, is the function that tells us the probability that a random variable big X is less than or equal to any little x from the sample space of X. And it can simply be defined, oh, that's not right. This should have an X on the top here. The sum from whatever is the smallest element of the sample space up to whatever little x you want to evaluate of all the probability mass functions. So if I want to know the probability of knocking down 3 or fewer pins in the first roll of a frame of bowling, I could take the probability of knocking down 0, add the probability of knocking down 1, add the probability of knocking down 2, add the probability of knocking down 3, and then stop. That's the probability of knocking down 3 or fewer pins in the first roll of a frame of bowling. And the cumulative mass function I will denote with capital F. So capital F is the cumulative mass function. Probability the random variable big X is less than or equal to little x. Probability mass function, denoted by little f, is the probability a random variable X is exactly equal, strictly equal to any little x that I choose from the omega of that X. And in the first roll of a frame of bowling, we can actually get a concise expression for the cumulative mass function. Big F is equal to the x plus 2 Fibonacci number minus 1 divided by the n plus 2 Fibonacci number minus 1. And that we can define a function in R called CMF that returns that expression where the function f is the Fibonacci function that we wrote last time. And you can see, rounded to 3 decimal places, the probability of knocking down less than or equal to any number of pins on the first roll of a frame of bowling. And of course, the probability of knocking down 10 or fewer pins on the first roll of a frame of bowling has to come out to 1. So it's good that if x is equal to n, this expression for the CMF is going to evaluate to 1. Yes? No. We'll get to that in a second. Cumulative distribution of function refers to continuous random variables, but it is the same concept. More questions?
Data can again be continuous or not.
Yes. So we're conditioning on theta here. It can be anything. Good. Keep them rolling. More questions? All right. So what is the difference in the cumulative mass function evaluated at x and evaluated at x minus 1? Yes.
Be the PMF at X, the value of the PMF at X.
Correct. So if let's say x is 6, what's the difference between the CMF evaluated at 6, which is the probability of getting less than or equal to 6 pins knocked down, minus the CMF evaluated at 5, which is the probability of knocking down 5 or fewer pins? It's simply the probability of knocking down exactly 6 pins. And that can be shown algebraically, but it's true for all CMFs. The first difference of a CMF is a PMF. The difference between any 2 consecutive evaluations of the CMF function is the PMF evaluated at the higher of the 2 values of x for any 2 consecutive x's in the sample space omega. So that's true in general. And that is perhaps more easily seen, although you probably have to download the slides afterwards to actually see, because this is too small. So here we have a bar plot representing the CMF, the probability of knocking down at most this number of pins. And we have lines in different colors connecting consecutive bars. So we just got through saying how much does one bar rise more than the previous bar? That's the PMF. And if we're doing it consecutive, then the difference between 2 bars is just going to, on the horizontal axis here, is just going to be 1. So if we're rising by the PMF and running by 1, the slope of these line segments is going to be the PMF. We rise by the PMF, we run by 1. Looking at it your way. We run by 1, we rise by the PMF. So the slope of the top of a line segment connecting two adjacent bars, the slope is equal to the PMF. Now that's a roundabout way of thinking about what the PMF is, but it provides the most direct connection to what we're going to do next, which is to talk about the case of a continuous random variable. So rolling on. Before we get to that, what's the probability a random variable x is greater than a and less than or equal to little x? How would we go about attacking a problem like that? Yes.
fx minus fa.
And why is that?
Because it's like it's just the area of the CMF and the ring minus the previous one, and we get exactly the x.
I think we have someone with a very good memory here. Well, to get you started, we can think of that probability as 1 minus the probability that x is less than or equal to a, or x is greater, capital X is greater than little x. So the probability of something is 1 minus the probability of it not happening. And there's 2 ways that this could be false. So 1 minus that. The probability that x is less than or equal to a is the CMF evaluated at a. And the probability that big X is greater than little x is 1 minus the CMF evaluated at x. So we do that, the ones cancel, and we get f evaluated at x minus f evaluated at a. So that was fun. And we just explained the same thing that we did. Okay, so we got like 10 minutes to generalize this to the case of a continuous random variable. This is the case where the sample space omega is some interval, such as all real numbers, or do we have an earthquake? All positive real numbers, or it could be some interval between any 2 numbers, p and q, where q is greater than p. Any of those are possible. The trick to continuous random variables is to remember that on an interval, there's an infinite number of points. So it doesn't really make sense for us to talk about the probability of a particular point when there is an infinite number of them. So if you just sort of take the naive view that all points have the same probability, you know, that would be like 1 over infinity, which is 0. So that doesn't seem particularly useful. So for a continuous random variable, the probability that it is exactly equal to any point with like an infinite number of decimal places of precision is defined as being 0. So that's what makes this whole extension a little bit complicated, and it's why we do it second. Nevertheless, as Sean pointed out, it's perfectly reasonable to define a cumulative function in the case of a continuous random variable. So the probability a continuous random variable big X is less than or equal to any little x from the sample space, less than or equal to. That is a very not vacuous question. We can denote that function again by capital F. But in the case of a continuous random variable, we call the capital F function a cumulative density function, abbreviated CDF. So there's really no conceptual difference between a CMF and a CDF, except CMF emphasizes the random variable in question is discrete. CDF emphasizes that the random variable in question is continuous. However, you will often hear sloppy people use CDF for both cases when they don't really care if it's discrete or continuous. Or there's other names for it as well. Like in the discrete case, the probability that a continuous random variable big X is greater than A and simultaneously less than or equal to little x is equal to the difference in the CDFs first evaluated at X and then evaluated at A. So we can just do a difference of CDFs there. And if we let X be equal to A plus some small number H, we can plug X, the CDF evaluated at X, which is A plus H, minus the CDF evaluated at A in the numerator. So that's how much we rise. And we put X minus A in the denominator. But since X is equal to A minus H, we're left with H in the denominator. And if we let H approach 0 from above, we have the definition of a partial derivative of the CDF. So CDF at A plus H minus CDF at A divided by H as H gets small. It's the partial derivative of the CDF. It's the slope of the line tangent to the CDF. It's the instantaneous rate of change in the CDF. All these things that hopefully you remember from calculus or pre-calculus, here defining the derivative of the CDF. And the derivative of the CDF, it's a function of X. It can change depending on what X you're talking about. And this derivative of the CDF has a special name known as the probability density function, or PDF. And the most confusing thing about a probability density function is that it does not output a probability. It is a function, so it's got that going for it. But a PDF is merely the derivative of a CDF. It's the slope of a CDF evaluated at a point. A CDF returns a probability. A slope of a probability function is not a probability. It's a slope. All right. Anybody have any questions about the distinctions between CDF and PDF or PDF and PMF? So in the discrete case, a probability mass function actually returns a probability. It is also the rate of change in the CMF. In the continuous case, the PDF is the rate of change in the CDF, but the PDF is not a probability. It's only a rate of change.
So when they in software like in R, there's a function called B norm.
Yes.
You can evaluate things at a point.
Yes. So P norm evaluates the CDF. I could also differentiate that CDF evaluated at the same X. That's the PDF of the normal distribution, denoted D norm. Yeah, so we'll get to that in R. So here is a picture of a distribution whose sample space is the continuous interval between 0 and 1 inclusive. The black line is a function representing the CDF, the cumulative density function. So the probability that you get less than or equal to 0.2 is whatever that number is, like 0.17 or something like that. Maybe higher. I don't know. In any event, CDF. CDF returns a probability, so it's a function that is bounded by 0 and 1. In this case, omega is also the interval between 0 and 1. But in general, a CDF can be, for any omega, any interval, but the CDF is always going to return a number between 0 and 1. And if we look at the mathematical expression for this CDF given by the black line here, it's 1 minus the quantity 1 minus x raised to the power of alpha, all raised to the power of beta, where alpha and beta are two unknown parameters. In this case, they're restricted to be positive in order for this to be a valid CDF. And this particular black line is evaluated for the case alpha equal to and beta equal to 3, although alpha and beta need not be integers. They can be any real numbers. To get the PDF, which is the derivative of the CDF, I simply differentiate this expression with respect to x. And so I'm going to get, beta down here and then use the chain rule. I'm going to get an alpha over here. The two negatives cancel out. And we're left with the expression for the function in the red here, which is the PDF for this particular distribution. Alpha beta times x to the alpha minus 1 times the quantity 1 minus x to the alpha raised to the power beta minus 1, which just results from using the power rule of differentiation and the chain rule to do that like 3 times. So I differentiate the black line, I get the red line, which is a PDF, and it is clearly not a probability because, from here over to here, it's greater than 1. And probabilities are not greater than 1. Ergo, the red line cannot represent a probability. It merely represents the slope of the black line evaluated at x. Just to quickly finish up, I know we're out of time. So the difference between a density function and a mass function, one, in the discrete case, the PMF yields a probability. In the continuous case, a PDF does not. So the PMF is bounded between 0 and 1. A PDF need only be positive. There's no upper bound to it. Indeed, it can be infinite. In the discrete case, we can sum the PMF to get the CMF. In the continuous case, we can integrate the PDF to get the CDF, just using the fundamental law of calculus that the derivative and the integral are basically inverse operations of each other. So there's some slight differences, but the similarities between a density function and a mass function are actually more prevailing. Again, we can use the multiplication rule either way. So the joint density of x and y can be constructed as a marginal density times a conditional density. Bayes' rule holds in the continuous case as well. So this is the particularly important expression for Bayes' rule. What's the conditional probability density function representing our beliefs about theta, conditional on data y and x? We can do that as the product of f of theta times f of y given theta divided by f of y. But we'll have to talk about constructing f of y because it involves an integral. And just like in the discrete case, the probability that x is greater than little x can be obtained by evaluating 1 minus the CDF at little x. So we'll pick it up on Thursday. We'll talk more about continuous random variables. We'll talk about expectations involving functions of continuous random variables and keep going from there. But if you have any questions before Wednesday, post them on Piazza, or Imad is going to have office hours tomorrow evening. Also, we'll be having a special session late Friday afternoon. It's only for those of you who've never used R Markdown before. So if you've taken a class from me, you don't have to show up. You know R Markdown. For the rest of you, this is the format that we're going to use for the homework. The first homework assignment will be posted tomorrow night. So we want to make sure everybody knows how to turn in the homework properly. Yes. It's going to be 2 sessions from 4:30 to 5 or from 5 to 5:30. It only takes about half an hour to learn it. Okay. Post questions.